Today we're going to learn about beats. We're going to learn about beats, and then we're going to do a bunch of conceptuals together.
Yeah.
Anybody here who went to music? Do you know what I mean by beats?
Like music beats?
Okay, music beats like the cadence of a song, you know. Okay, well, there's something else. There's another meaning for beats. Have you ever been like singing a note and the person next to you is singing the same note, but you guys aren't singing precisely the same frequency? So you hear a wah 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 while you two are singing the note. How many people have ever experienced that? Okay, well, in musical parlance, those are called beats. That happens if you have two like wind instruments and they're not completely in tune, so they're playing the same note, but it's not really the same note, and again, you'll get those beats. Wah, 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 wah. Well, I'd like to have you experience beats, so I'm going to play you a couple of waves that are very similar but not identical frequency. Okay? Can you guys hear that okay?
Yeah.
That's 1,000 hertz. By the way, have I ever gone up the frequency scale to see how high a frequency you guys can hear?
No.
Oh, let's go ahead and do that. Here, we'll do that right now. Okay, that's 1,000 hertz, right? I can't go low because I don't have good enough speakers. Supposedly you can hear as low as 20 hertz, but these speakers can't do 20 hertz, so it's kind of a waste. You need big speakers, what's called woofers or subwoofers, to allow you to hear really low frequency because it takes a lot of air to be pushed. Okay, that's 1,000 hertz. You guys hear that okay? That's 9,000 hertz. Can you guys hear that?
Yeah.
Good. I can hear it too. Can you hear it, Anise?
No.
You can't hear it? Are you serious? Can you hear that?
Yeah.
7,000. Okay, just a second. Can you hear that?
Barely.
Did you have injury to your ears sometime in your life?
I don't know, but even when I was younger and we would do those like, oh, hear the beeps, I can't hear beeps. I don't know.
And you let them know you couldn't hear them?
Yeah, and they were just like, let's try it again, and they would do it again, and then I would like somehow pass. Yeah, last year Haggerty did the same thing for anatomy.
Yes?
And everyone's like, oh yeah, I can still hear it, and I was like, I stopped hearing it like 4 rounds ago.
Wow. So let me do that. Let me just turn this off for a second. So Anais, do you sometimes have trouble understanding what people say?
Yeah.
Like someone says, hey, I want to go to the trestle and pay my toll, and it just makes no sense to you. Okay.
I say huh frequently, and usually based on like the context of the situation, I'll know, and it'll take me a second. But yeah, people have to repeat themselves a lot.
Right. So yeah, there's something bad with your hearing. Like you have the hearing of an old lady. Hope you don't mind, because that's what we people my age always have to deal with. And so that's why this new habit of young people. Did you know young people talk much quieter now than they did like 20 years ago?
Really?
I don't know. It's become, yeah. You talk to young people and they mumble. All you young people mumble. Where like 20 years ago, young people were always too loud. You're talking too loud. Not anymore. They all mumble. You know, and so you're gonna have a lot of trouble listening to your friends when they all mumble.
Yes.
Oh my gosh, Anise. Okay, well, this is the first time in my career that I had a student with worse hearing than me. Yeah. Okay, here we go. Here's 9,000. So you guys all hear that except Anise. Okay. Here comes 10,000. Can you guys all hear that?
Yeah.
Okay, that's about when my hearing cuts out at 10,000 hertz. So now I got to get back up to 10,000 hertz. Okay, here comes 12,000 hertz. How many people can hear that?
Oh, you're
Yeah.
cool.
Yeah, exactly. Me neither. They're all dogs. Okay. How about I'm gonna go up to 16.
Oh, it's not.
How many people can hear 16,000? Oh, good for you guys. You can't, Cheyenne?
No.
Okay.
I think in very last year, mine cut off around like 15, I felt so weird because everyone else was like, I can hear it. And I was like,
Wow. And who did you have last year? Mr. Lotta, of course. And so how did he do that? Did he do it with like his cell phone?
Use like that speaker. Up there.
Okay, so he essentially had something on the computer. Yeah, I just use this because it's more convenient. Okay. Okay, here we go, 18,000.
Oh yeah.
Can you guys hear that? Who can hear that?
Raise your hand.
Okay, so some of you can, of course. Here comes 20,000. Can anyone hear that? Okay, that's if you're a human being. That's about when your hearing cuts off. If you're part dog, you can hear that. Anyone hear part dog? Good. Okay. Well, that's it. Great.
I'm a dog.
You can hear that?
Okay. Well, it's now time to talk about beats. Okay, you can hear that tone, right? And it's just a constant tone, okay? But now I'm going to play another tone along with it. A tone, oh, and by the way, I can even show you the waveform. You guys see that waveform? That's just a sine wave, it's just a tone. It's about a 1,000 hertz tone. But I'm now going to play another tone of similar but not identical frequency. Can you hear those beats?
That's interesting.
And you hear those variations in amplitude? You might think of them as wah-wahs.
Yeah.
Okay. And the closer the two tones get together, do you notice the lower the frequency of these beats? They're right on right now. The two frequencies are identical. But if I go a little bit away, and you get beats when the second tone has a lower frequency or a higher frequency. Okay. I want to now show you what the waveform looks like when we look at several periods of that waveform. Wait. Right. Are you seeing that okay now? Where essentially those beats you're hearing are alternating high amplitude, low, zero amplitude, high amplitude, zero amplitude. So that's what beats sound like. And of course, if the frequency of the beat decreases, that means the wavelength of the beats is going to increase. That's very high frequency beats. Lower frequency beats. Okay. So do you guys believe in beats?
Yeah.
You okay with this?
Yeah.
All right. But when I turn off the one tone, then you just get the other one and there's no beats anymore. All right. So here comes the definition of beats. Beats. Or you might think of them as wah-wahs. If anyone has an electric guitar with a wah-wah pedal, what a wah-wah pedal do is give you variations in amplitude. If you want variations in frequency, you're going to have to use the whammy bar. So you can go wow, wow, wow. That's the whammy bar. The wah-wah pedal goes wah, 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 but it maintains the same frequency. And the beats are the wah-wahs. Okay? And so these are variations in amplitude. Variations in amplitude, that is loudness and softness. Variations in amplitude. Variations in amplitude when two waves of similar but not identical frequencies interfere. That's what beats are. The next thing I want you to see is that beats are an entirely mathematical phenomenon. Oops. Oh wait, that went off. Oh, okay. Just a second. So here's what I'm going to do. I'm going to actually just graph two sine waves, two waves of similar but not identical frequency.
What?
Do you see this first sine wave is just y equals the sine of x? If you remember from trigonometry, that means the period is 2 pi. I'm sorry, the period is b over 2 pi, so the period would be 1 over 2 pi. Okay? Here, and thus the frequency would be 2 pi. Here, this is sine of 0.9, which means the period would be 2 pi, rather 0.9 over 2 pi, or the frequency would be 2 pi over 0.9. So this wave will have a slightly higher frequency. Okay? Well, let's go ahead and graph them. Here comes the first, here we get, okay, and wait, I gotta do this. 10 pi, okay, good. Right, here comes the graph. Here's the first wave. This is sine of x. Here comes the second wave, sine of 0.9x. Okay? I want you to see these two waves initially. What kind of interference are these two waves experiencing? Constructive or destructive?
Constructive?
Yeah, constructive. They're in a phase. But after a while, what kind of interference are these two waves experiencing now?
Destructive.
Destructive, yeah, because one of the waves is lagging behind. They get to be 180 degrees out of phase. And now you get destructive interference. Here, let me actually get us more waves on there. So let's go with 35. Here's the first wave, sine of x. Here's the second wave, sine of 0.9x. I know this is a very busy sort of graph, but I just want you to see again, here I'm getting constructive interference. You only see the one wave. Or over here, I'm only getting constructive interference, right? The two waves are completely in the phase. But when I get over here, I'm getting destructive interference now. The two waves are 180 degrees out of phase. Well, let's see what happens when I add them. And again, this is all mathematical. I'm not listening to music or anything. I'm just adding a couple of sine waves. Okay, here we go. Do you see it that I get that wave pattern that you were seeing on the oscilloscope? I'm getting a sound that goes from loud to soft to loud to soft. And those are the beats, those variations in amplitude. Every one of those wah, 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 wahs you hear is the maximum amplitude that you're getting from these beats. You know? You guys okay with that? So that's all. It's just a completely mathematical phenomenon. It happens when you add two sine waves of similar but not identical frequency. Okay? Well, hey, let's go ahead and do a little bit more math for these guys. And I won't need this anymore, so I will plug in my microwave. So I can Okay. Do you remember when I was demonstrating the beat frequencies, the closer the frequency of the two waves got to each other, the lower the beat frequency got? It would go wah, 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 wah. But when the two frequencies got close together, it would go wah, wah, wah. So what do you suppose the formula, if I let F1 and F2 be the frequencies of my two waves that are interfering, what do you suppose the equation for the beat frequency is going to be? What do you suppose the relationship between the frequencies of F1 and F2 is going to be to the beat frequency? I want to remind you again, when the two frequencies were identical, then there was no beats whatsoever. The beat frequency was 0. And then as the two frequencies got farther and farther from each other, the beat frequency went higher and higher. Yes, Earl? I know you know.
Difference in frequency.
Thank you very much. It's the difference in the frequencies. And I'll put absolute value in the difference in the frequencies because one can be higher or lower and it doesn't matter. You still get those beats. See, Earl, I'm just going to call on you. Whenever no one wants to answer, I'll just say, Earl. Okay, so let's say, is there someone in this class who actually can sing well? Oh, Anais, you sing well. We did.
No, no, you don't.
We did karaoke together. No, you can't.
Go, Gavin. I can sing, but not well, I'll tell you
Okay,
that.
well enough. You can hit a note. So let's say Anais sings, and she sings a 300 hertz, 20 hertz tone, and I'm singing with her. We're doing karaoke, but I am genuinely not that great of a singer, especially now that my voice got thrashed from 30 years of teaching. And let's say I sing a 323 hertz tone. You tell me, what's the beat frequency? How many people are thinking 3 hertz? Yep, you're going to get wah, 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 3 times a second. Yeah, beat frequency equals 3 hertz. Good. Okay, so let's do a different version of this type of problem. Let's say you've got a guy who's a piano tuner. That's his job. He tunes pianos and fixes them up. But he's old school. He's an old guy. So he tunes pianos not by using electronic equipment. He uses a tuning fork and his practiced ear. And so this piano tuner has a tuning fork that's 440 hertz. Concert A for you and me. He then plays the note and listens to hear the interaction between the note he's playing and the tuning fork he's using. And he hears beats at 4 hertz. So he hears 4 hertz beat frequency. Tell me, what's the frequency of the note that he's playing? Someone tell me. Yes, you have a tuning fork. There, listen. So how many people thinking 444? Yeah, that's not too hard. 444 hertz, right? Is there another choice though?
330. Yeah.
What's that?
336.
Yeah, 336. I'm sorry, 436. Did you say 436. Yeah. So you guys okay with that? It could be either of those. And now, of course, he can tell the difference because he can tell between sharp and flat. He's got this incredibly, practiced ear. But let's say we can't tell the difference. So we tighten the string. We tighten the string. And now the beat frequency becomes 5 hertz. We tighten the string and the beat frequency becomes 5 hertz. Tell me, what's the frequency of the note now, right now? Now that the beat frequency between this note and the tuning fork is 5 hertz, what must be the frequency of the note? Please think about this for a second, then we'll have a vote. Alrighty, time to vote. The beat frequency becomes 5, so you've only got 2 choices, 435 and 445, right? How many people here say the frequency of that note must now be 435? How many people say 445? Oh, okay, someone explain to the class. Why is it 445? How did you know? Yes, Anais?
When you tighten it, the frequencies get higher, so you know it's moving up.
Okay, great. Anybody else want to add to that? His frequency's getting higher? Okay, well, let me ask you this. Here, I'm gonna give you another one. I didn't give this last period. We loosen the string. We loosen the string, and the beat frequency becomes 5 hertz. Now, what must be the frequency of the string right now? If it was 4 hertz beats, so it's one of those guys, then we loosen the string and now the beat frequency becomes 5 hertz. Well, how many people think it's the other one, 435? How many people think it's 445? Okay, anyone wanted to explain to the class, why is it 435? How do you know? Someone explain. Yes, Maxwell?
Since you're loosening up the string, the frequency we have decreases, so it has to be 485 and not 445.
Okay, good, good. And then I'm gonna give you one, I don't know if I'm beating this dead horse. I'm done. Okay, hey, guess what? There's one more thing I need to tell you about beats, about the combining waves of similar wave frequencies. So suppose Anais is singing 320 and I'm singing 323, but I don't know if you noticed when I put the sum of the wavelengths on the screen, it was one single wavelength. And if it's one single wavelength when I add 2 waves, that means there's only one frequency. And that's the frequency that the audience hears. The audience doesn't hear her or me, although probably can distinguish our notes somewhat. But there's going to be a tone that the audience hears that's neither 320 nor 323. What do you suppose the tone the audience is going to hear is? What's that?
The average of your.
Thank you, the average of them. Absolutely. The audience is going to hear 321.5 hertz. So what happens is, if Anais is singing her note perfectly and I'm singing along 3 hertz sharp, I make us both sound sharp. The audience thinks we're sharp. Well, really, it's just my fault, but it doesn't matter. They hear sharp. This is why we used to have a band director here at Etiwanda High School. His name was Don Jaramillo. He is now our principal. But back when he was a band director, my students tell me that he used to say, it's more important to be in tune than to be loud. He would always tell that to his players. And the reason is, of course, this. One instrument can make an entire orchestra sound flat or sharp. So everyone has to be in tune. It's incredibly important. Anyone who's ever attended a classical music concert, what's the first thing all the players do before they play? Yeah, they tune. They got to tune to each other. If they don't, then one bad guy makes them all sound bad. So that the frequency of the combined waves is F1 plus F2 over 2. I mean, it's just the average of the frequencies. Okay. Then hey, we're done with beats. Now we're going to do conceptuals, but we don't have to tape that. So, right?